Gyronics.
Hello everyone, my name is Jairo A. Madrona and my course is MSECE. Today I will be presenting my project proposal in numerical methods entitled The Numerical Analysis and Modeling of Shockley Diode Equation with Temperature and Voltage Variations. And this will be my topic outline. First, I will discuss briefly the Shockley Diode Equation, then the methods or the steps I have applied to model the Shockley Diode Equation. Specifically, I use the finite difference method to model this Shockley Diode Equation. And lastly, the numerical analysis, which is based on the MATLAB results of using finite difference method as a model. Okay, so first is the Shockley Diode Equation. This is the Shockley Diode Equation. So the I stands for the current, so as a function of V, which is a voltage across the diode, and temperature in Kelvin. I sub 0 is the reverse saturation current, and Q is the electron charge. N is the ideality factor, which is either 1 or 2, and K is the Boltzmann's constant. And using this exact solution, if you are going to graph this equation, you will end up with a graph like this one. And of course, we are expecting the same result. So let's proceed now on the methods I have applied to derive the numerical approximation of this Shockley Diode equation. First, I transform the Shockley Diode equation into its partial differential equation equivalent. So using the exact solution, the partial derivative of I, with the current I with respect to voltage V, is this one. So I let sigma, so this one, equivalent to Q over N times K. So these are constant. So to simplify my equation, so I group that constant. So this is the partial derivative of I of current with respect to voltage. Okay. And next, I also convert the Shockley Diode equation as a partial derivative of current with respect to temperature. And this is what I get. Okay, so again, the sigma is equivalent to this constant. Okay, so you might wonder why I transform the exact solution. So I have the exact solution. So actually, there's no need to convert it into the partial differential equation, right? So the purpose why I convert that exact solution into PDE is to simulate, okay, the real-world problem. So where an analytical solution may not be feasible or practical. So I am creating a scenario here that suppose you don't know the Shockley Diode equation, right? All you have is, let's say you have diode, you apply voltages, you measure current, you vary the temperature, you have this data based on the experiment, okay? And of course, that's your problem. You don't know the exact solution for that. So in real world scenario, you cannot directly derive the exact solution from that experimental data, right? But you can model it using the differential equation. Okay, so just assume again you have that data from the experiment and you derive this one. So you know the partial differential equation, but you don't know the exact solution. And that's a problem you have right now. Okay, so let's assume we know the differential equation, but we don't know yet the exact solution. And in this case, again, let's assume that the solution is not feasible and quite impractical. So all we have to do is to apply the numerical technique to solve or to approximate the solution for this PDE. Okay, so that's why I convert again the exact solution into PDE. So just to simulate the real world problem. Okay, so that's my purpose of converting the Shockley Diode equation to PDE. So the next step is I will apply one of the technique, the finite difference method, to model that partial differential equation or to approximate the solution. So I'm using here the forward difference approximation of I. First, it's with respect to V, voltage. And of course, I will start with the Taylor series expansion of current around V, or around the voltage. And I will assume the second order to 0. So that's my error now. My error is in second order. And we can rearrange the solution. We will be calculating the rate of change of current with respect to voltage. Okay, so the next equation would be this one. So, transfer this I to the left side, then divide by delta V. Okay, so this is the I. And we know from our PDE, so this is the partial differential equation we derived earlier, that the rate of change of I with respect to B is equivalent also to this equation. So we can substitute that. Okay. And we have now this next equation. Okay, next step is we will be calculating the next value of I. So using the current value. For that, we'll cross multiply this change in voltage with delta B to the right side, then transfer this I to the right side. And we will end up with this equation. Okay, so we have I subscript j plus 1. I just remove the function of B to simplify the equation. But take note, this is I as a function of V sub j plus 1. Okay, so I just remove the letter V. So the same with this one, this ij is similar to this one. That is I is a function of V sub j. So I just simplify it into I sub j. But take note that is a function of V. So this is the equation I have derived. And this is the equation we are going to use to approximate, okay, the values of I. Of course, using MATLAB. And this is the snippet of the code. So I have used in MATLAB. Okay, so this is the first value of current, called 0. So we will iterate the value of current from 1, initial value, up to n. So n is the number of grid points. And I set this into 1,000 grid points to make it more accurate. Okay, so this is the iteration statement equivalent to this equation. So next, the same concept, but this time using temperature. So our current varies with temperature. Again, we will be using the Taylor series expansion, and we will equate this to 0, the second order. So we have a second order error again, and we will equate again in terms of the change in current with respect to temperature. And we know from our previous partial differential equation, the partial derivative of I with respect to t. So we have this equation, and we can equate that to the left side of this equation. So we have this again, and we're going to calculate the next value. So the same process, cross multiply this delta t, then transfer this I to the right side. By the way, I'm using subscript n for temperature. Okay, so to differentiate the voltage and temperature. For voltage, I use J. For temperature, I use N. Okay, so we have this equation again. And again, take note, this I. So I only simplify the notation. So just take note, this is a function of t. So the same with this one. That is I is a function of t. Okay, I sub n. So this is the equation we're going to use again to approximate the current with respect to t. And this is the snippet of my MATLAB code, but this time instead of 0, the initial value of approximate current, so I set it the same with the exact value. Okay, so which I don't think it doesn't start with 0. And this one is the statement, which we're going to iterate from the initial value up to the n value. This is the grid points, number of grid points. Again, I set this to 1,000. Okay, so this is the equivalent MATLAB script for this equation. And this is the result of this finite difference approximation. So we have now the numerical analysis. Of course, it's based on the MATLAB result. So first is the change of current with respect to voltage. So this is the current voltage curve. And as you can see, okay, the finite difference method closely aligns with the exact current values. So I plot the finite difference method, then I also plot the the given Shockley's Diode equation. That is the exact solution. So this one is the approximate solution. So the finite difference method. So they are closely aligned. But of course, there's some error for that since this is only approximation. And for that one, I analyzed the error. I set the temperature to 298 Kelvin. So this constant, I set it to constant temperature. Then I vary the voltages. And the average error for this one is 0.97%. So that is acceptable error, right? By the way, the average error is, there's some error, okay, as I increase the voltages. So the average of these errors, okay, so that is 0.97%. Then I increase the temperature to this time 373 Kelvin, and the error reduces to 0.78%. Then under one, I increase again the temperature to 423 Kelvin, and the error reduces to 0.68%. So the conclusion that we have based on the trend, so the higher the temperature reduces the error. So between the approximate and exact solution. So as you increase the temperature, the approximation error also reduces. Okay, so the next one is the result, this time the response of current with respect to temperature. And again, as you can see, okay, the finite difference method is closely aligns with the exact current values. But of course, there's some error again. So for the error, this time I set voltage to constant. So let's say at 0.3 volts constant voltage, then I increase the temperature. So the error is 1.24%. So actually this is the minimum error I have at 1.24%. Since if I'm going to increase the voltage, let's say at 0.7 volts, the error also increases, so to 6.01%. Okay, so the next one is I increase from 0.7 to 1 volt. Okay, so the error, okay, that's huge, 20.48%. And one interesting thing here for the curve is this one. After 320 Kelvin, so the error seems flattened, doesn't increase anymore. Okay, for this graph. But as you can see, the error is huge at 1 volt, 20.48%. So this increase demonstrate the method's decreasing precision at higher voltages. So my hypothesis for this one, why the finite difference method cannot approximate the response of current at higher voltages is, we go back to the Shockley's Diode equation. Actually, this region here is called the transient state. So the current starts at 0. So as you increase the voltages, this is the behavior of the diode in actual application. Ideally, if diode is silicon, it will need 0.7 volts. That is the barrier potential. So after 0.7 volts, the current will start to rise. So it will increase to the maximum current. So actually at this part, after that 0.7 volts, ideally that's 0.7 for silicon, the diode is now in the steady state condition or region. So from transient, okay, so it will now in the steady state region. In steady state region, the diode acts like a linear circuit. So that's why the finite difference method cannot approximate accurately if the voltage is at 1 volt. Again, the diode at this point acts like a linear circuit. But that's my hypothesis only. So it needs verification. Okay. Anyway, in conclusion, the findings highlight the finite difference suitability for modeling semiconductor behavior within specific ranges. But also, it demonstrates its limitation in high precision applications under extreme voltages or temperature conditions. And also the MATLAB simulations, so wherein we compare the finite difference method results to the exact analytical solution, suggest exploring some of the numerical techniques, right? Not only the finite difference method. So to improve accuracy for modeling semiconductor devices in highly nonlinear regions. Additionally, so I recommend to implement also the appropriate boundary conditions that is specific to a physical constraint of the device that can enhance the reliability of the numerical results. So some diodes will limit their current up to 1 ampere only. So maybe we can create a boundary condition for this one. So let's say the numerical techniques only valid from 0 to let's say 0.9. Okay? Because as you can see at this point, the error is 20%. So it's very high. So these are some of the suggestions to how to improve this numerical modeling. Okay, and that's all. So again, my name is Jairo A. Madrona, and thank you. So this ends my presentation for my project proposal in numerical methods.